Okay, so our goal this time is to apply L'Hopital's rule and understand how to use it in a graphical situation, okay? Understanding things graphically is, you should strive to do that behind everything in calculus. And mathematics in general, too, that's not a bad idea. So we don't want to just, and we can't, in fact, just blindly go ahead and apply L'Hopital's rule in this situation. We need to check hypotheses, and we need to make sure that we understand what L'Hopital's rule is doing. So L'Hopital's rule is replacing functions with their derivatives, which is basically a tangent line. And we can think of that as in the process of zooming in, right? That's our intuitive understanding of L'Hopital's rule. So the function we have here, let's move this up a bit, is f of x, okay? And we know that it's differentiable. We have a tangent line right here. So evidently this is the tangent line at x equals 0, right? So one thing that I'm going to say from that right away, let's just draw, put some facts together. What does it mean about the value of the derivative of f at 0? That this is its tangent line. Since the tangent at 0 has slope 3/4, we know that f prime of 0 is equal to 3/4, right? That's the meaning of the derivative here. Okay, like the most basic fact of Calc 1 there, okay? So make sure that sort of thing isn't stumbling you up. If you are, at all shaky on the concepts from Calc 1, then that's where there might be problems, because we don't have the time or coverage in Calc 2 to go over that stuff, okay? You will be able to improve your algebra and integration skills in this course, but not stuff like that. Okay, so we have its tangent line, which basically means this for us here, tangent line at 0. And we also know that f prime is continuous, okay? So let's take a look at this limit right here, okay? Is it in an indeterminate form? Well, yes, actually, because we see that the graph right there is 0, 0, f of 0 is 0. F of 0 is equal to 0, right? So the limit as x approaches 0 of f of x over 1 minus e to the x, we get 0, we get 0. This is an indeterminate form. Oops, should put it there. Okay, an indeterminate form is a dead end, algebraically. We can't work with 0 over 0, okay? 0 over 0, I should actually point out that this notation here, equals sign, this is a bit of an abusive notation. However, it's common for people to write things this way, okay? It's not actually equal to 0 over 0, because 0 over 0 isn't equal to anything. It's undefined, okay? All right, so because of this, we get an indeterminate form. The denominator here is also going to 0. Maybe you should say some words about that. Why is the denominator going to 0? Is that clear to you? Well, I can calculate it like this. What is it that lets me calculate things like this? This step right here is the crucial one. What lets me do that? I reviewed it in the previous 2 videos subtly. It's something that comes up in chapter 1, chapter 1.6, when you're talking about limits in calculus 1. What's the simplest way you can evaluate a limit? It's when it's continuous. that's what lets you substitute in a value in order to evaluate a line. Okay, things like that you might have forgotten from Calc 1. These are all important to being able to make heads or tails of anything that we're doing here, okay? So when things are smooth, you can take a limit of them and you can just plug in the value. Smooth is continuous in this case. Yeah, we've got an indeterminate form. We know that f is differentiable, so we are going to be differentiable near a, and g prime of x needs to be non-zero near a. Okay, so how about this? Limit, excuse me. The derivative. The derivative of the denominator needs to be non-zero. So if I take the derivative of this, I get minus e to the x, which is always a negative number. It is non-zero everywhere. Okay, so everything that I've been doing here in these lines is nothing more than just evaluating the hypotheses. These are differentiable. The denominator is non-zero, the derivative of the denominator is non-zero, I mean, and the limit we're taking is an indeterminate form. Okay, so because of all this, L'Hopital's rule applies. Okay, that's all just verifying the hypotheses there. Okay, so make sure you are doing that. Verify hypotheses. Okay. Right, now that means we can use L'Hopital's rule. So that means I can do this. So let's go ahead and do it. So the limit, this limit here, the one we're trying to work out in the problem statement, will be equal to the limit as x approaches 0 of f prime of x over minus e to the x, right? Take a look at that. All I'm doing there is fit it on screen. Taking this limit right here, that's f over g. So on the right-hand side here, I replace it with f prime over g prime. So there's the derivative of the numerator, it's f prime. There's the derivative of my denominator. Okay. So the last bit is actually doable by the quotient rule. This is the quotient rule from Calc 1, chapter 1.6. And actually, I'm falling into bad notation here. I should go this way. Working down is generally better than working across because top to bottom is an obvious order of progression. Logical steps happen in order, so top to bottom happens in order. Okay, so yeah. This is by the quotient rule. So that's what I told you earlier to review from chapter 1.6. Okay. So what's the evaluation of the denominator? Well, that's actually one that we did before, just like this anyway. It's continuous. So the denominator, we get minus e to the 0 because it's continuous. What do we get in the numerator? Well, actually, that's continuous too. Okay? So because we know those two things are continuous, we can just plug in the limit one. Because both f prime and the denominator u to the x minus e to the x are continuous. Okay? So that's basically the end. just plug in the values for these things. What is e to the 0? E to the 0 is 1. We did that before. What is f prime of 0? Well, that's actually an observation that we made up here, just a very simple one from Calc 1. What does it mean for the slope of the tangent line to be 3/4? Well, that's f prime of 0. Okay, so it all comes together. We were able to evaluate this limit using the graphical properties here. I really like this problem because it's got all of these very important ideas. Continuity is ever important. The idea of what a derivative is to a slope of a tangent line. We've got to worry about the quotient rule here. Okay, everything in here is just great. So you should plan on making sure you understand this problem.